Any other questions? Okay, let's so I will so we are doing 4.3.3, right? That's what we did, except that we didn't quite. So let's do it again in a different language. So what are we saying? So x is, let's assume x to be an irreducible variety. Let's see what all we are saying. So the point is made reduced to the affine case easily. So that we saw last time. In any case, I will not insist too much on this because we have not even defined formally a variety. So just assume that we are in an affine case. So what are the points I want to make? So there exist simple points. Finally, at the end of the day, after you close the book and want to think about this, what are we getting? That there are simple points or smooth points. They do exist. In fact, there is most points are smooth. This is what you want to say. So there exist smooth points. In fact, the set of simple points is an open, non-empty open, non-empty subset. This is what you want to say. Okay. Moreover, so if I look at dimension of the tangent space to x at a given point x, so let's put K here, that K is our underlying algebraically closed field, then this is always bigger than or equal to dimension of x for all x in x. So what we are saying is the tangent space dimension is always bigger than or equal to the dimension of the variety, and it is equal at most points. This is what you would say at the end of the day. But there is a little bit extra here. Okay, so and the little bit extra is, if x is a simple point, there exists an affine open neighborhood U of x such that the universal module of differentials, right? So remember that this notation is, by this we mean, this is short for Ku over K. Ku makes sense. Ku is an affine variety in its own right, so that makes sense. So Ku is a free, is a free Ku module with a basis dg1 dge for, okay, so E is equal to now dimension of x. This E stands for the dimension for suitable GI in K. Okay, this is what we want to say. Okay, now for a moment let's forget the last one, let's just look at this earlier ones. Okay, I'll assume X is an affine variety. So the point is, so if I write this, so assume X is affine. And then you look at recall construction, not construction, but okay, I'll call it construction of by construction I don't mean the formal construction, which is as I mod I square, but rather the one where we took a free module and went modulo certain relations. Okay, so if we do that, then we have something like this. You have kxm, kxn, where we are thinking of x as sitting inside a n, and then the ideal of x is generated by a certain set f1 through fn of polynomials. Okay, and this you would write del f1 by del x. Okay, let me use t here because otherwise there is too many x's. So del f1 by del t n. So t1 tn are a set of affine coordinates on this affine space, and then this is del fm by del t1, del fm by del tn. Okay, so you write a matrix like that, and this is given as that's an exact sequence, and this is the co-kernel of this one. Okay, so what is meant by, so then our notation was we called this matrix A, and then we wrote something like MA to be the co-kernel of that map. That's equal to is what we know from construction. Okay, right. So moreover, we also know that, okay, so the point is let R be the rank of this A over Kx, that's what is rank. Ranks always make sense over fields. Okay, so I do that. So some observations to make are that here's the first one. If I take this, that's observation 1. Right, we have seen this all, but I always, if you close the book and wanted to think about it, so that's one observation, right? You can think about it as being, to prove that, you could think about it after homing into some m over, so that equality is as kx modules, right? As k round, the field k round bracket x modules. So to say that two vector spaces are the same, there is at least a map one way, and you want to say that map is an isomorphism. So you hom it into some arbitrary vector space and show that the resulting map is a homomorphism for an arbitrary, after you hom it into an arbitrary thing, and that the exercise is, of course, that you have to check yourself, that if that is so, then the original thing is an isomorphism. Okay, and once I hom it, I do get, I have translated into something into differentials, right? So it amounts to saying derivations of as a kx, k derivations, if I am given M is a kx vector space, right, and I look at k derivations of kx into M, that's the same as, I mean, I'm writing equality, but maybe I should write isomorphism, kx derivations from kx to, sorry, k derivations from kx to. Right, that's an elementary thing using this quotient, once you know the point is that not only if I know them on algebra generators is the derivation defined, is the derivation determined. So, okay, what is the derivation? The derivation is from an algebra to a module over that algebra. Now, if I know the images of algebra generators, then I know the derivation, because by Lipschitz rule, I know it on every polynomial. Okay. Moreover, even if I know it on field generators, then I know the derivation that is determined because of the quotient rule. Right. So here, while I have no new degree of freedom, because whatever generates here as an algebra generates there as a field. So I have no extra degree of freedom. That's roughly the proof. Okay. So because of this is true, right? Okay. So next, what you know is that, so observation 2 or theorem 2, right? Recall is that if I have, or let me say it like this, is equal to transcendence degree of kx over k, because, so of course this is equal to dimension of x. This part is, basic algebraic geometry, which I am going to assume. Okay. Now this is because K is algebraically closed, so perfect. So kx to k, kx over k is separable. I will just say separable, I will not say separably generated, right, because we've seen that those two are now equivalent. Now that's I want to remind you that's a rather non-trivial statement. Okay, it required some proof. So we have that. These two are the observations. So this is an observation. There is something to do here. It's not entirely trivial. This is even less trivial. Okay, there's something more to this. Okay, given all that, what do we know? I tensor this, right? What do I know? I know that from this, I know that when I tensor this, I get the presentation of this over kx, right? And therefore, I know that the dimension of this must be equal to n minus the rank. Right? So I know that so I tensor this with kx, right? It is exact because tensor product is right exact. Right? I just tensor this, which means I have this field. This becomes the field. This matrix stays the same. This becomes the field to the power n, and becomes a vector space. Right? Now this vector space, of course, becomes this. It is this, but it is equal to this. So I can think of this one here. But then now I'm over a vector space. What is the cokernel? It is n minus the rank of this matrix. Okay. So what we have is therefore, and on the other hand, that's equal to dimension of x by this. So we have proved that dimension of x. So what we have proved is that dimension of x is equal to n minus r. This is what we have proved. So we've related the rank of that matrix to the dimension of x. Rank is this, r. R is by definition the rank of this matrix. Okay. N is this n. So we've gotten a relation between n, the ambient. Of course, n could vary with n is not intrinsic to x, right? Neither is r, but they adjust themselves so that this difference is always the dimension of x. Okay, this is intrinsic to x. Okay. 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 Now, moreover, let's also prove. Let's observe that okay. So I'll erase this one, but not the statements. I want to say that I take omega x tensor that makes sense because this is a kx module, right? Now this I want to say is want to claim that. Okay, so let us see why this is. So what is this? So this was derivations. See form. So LHS. This star is of course over, by that is meant over this Kx. I'll write home as K modules of right, by definition the dual is that. Okay. Of course, you can see I should technically write a Kx here, right? But I can write a K. K, I have to write K sub x to begin. That is the actual definition, right? But I can remove that x and write a K. Because the map from K to Kx is an isomorphism. So K is sitting inside Kx, is mapping to Kx, and that one from K to Kx is an isomorphism. Right? So I'm doing some identification. Now this is the same as Hom Kx. Okay. Let me go ahead and write that. Okay. Right. Sorry, I'll write Kx. I do want K. I know that's actually better. No. We're just writing down literally the definition. Okay. So this I claim is the same as okay, the reason being the following. So this is abstractly, if I have, so let's say I have a algebra A, I have commutative, all algebras are commutative. I have another algebra B, right? And I have a B module M, and I want to look at Hom as B modules of, so let's say I have another algebra N over A, module N over A. Right? Now I could tensor N with B and make it into or let's put it in front just to make. So I extend scalars to B and write this. Right. But that is the same, I claim, as Hom A N to M. We've used this already in see, if you remember that exact sequence 15, what was numbered as equation 15, we had this last bit here had if you remember, we had F and an E prime and an E. These were extension fields, and we had E over F, right? And sorry, F, and there was E over E prime, right? Let me see if I get this right. Is this correct? So because there will be from E to here, there will be an F derivation, and so this from here to here there is an E prime derivation, and since it's the E prime derivation, it's definitely F derivation, and therefore by the universal property of this there is a map. Okay, right. So this is correct, and then there is here E prime over F, right? And then this is only an E prime module, right? And so the way we proved that this was an exact sequence was by harming it into E, and then observing that on the set of derivations it is easy to see, it's evident. And there, in translating this, what did we do? We wrote harm as E modules of this tensor product into a E module or E vector space M was the same thing as, so you wrote this was the same thing as harm of E prime of this into M, and then you got some derivative, right? That's how. So we used this that this, right? And this is, so why is this? I mean, this is so how do I get this map, right? So where do I send N? I look at one tensor N, look at its image here, and so there is a map this way, right? Okay, maybe I'm not saying it very well, but at least intuitively it's clear that why this is sitting inside this. It's because to get something here from here, like I said, you just take one tensor and look at where it goes, and that's where it goes. And once I know where N goes, it is defined on this, because yes, exactly, the N generates this as a B module. So once I know the images of where N goes, it's clear, the module map is entirely determined. So, right? Okay, but what is that? By the universal property of this, what is this? So can I erase this now? This bit? So this bit was used to prove this equality, right? So I'll leave it for a minute. So this is now equal to derivations. So please tell me, what should I write? K derivations from Kx to K, but what is that? That was one of the three or four descriptions that we had. Right? Okay, so we've observed that. So notice that it's a question of, I'm here talking throughout, so whether it's a simple point, the dimension, etc., whether I am talking about the dimension of Txx or the dimension of this, it's the same thing, right? Because I can, instead of talking about the dimension of Txx, I could talk about the dimension of this, right? Now, but what is the dimension of this? That's the dimension of n minus whatever rank I get after I tensor this with k sub x. So I take, so what is the, okay, so observe that what is here, this inside here, how do I get it? I can tensor this with k sub x, right? And then again it is exact, no problem, because tensor product is right exact. And therefore I would have gotten a presentation for this as that same matrix. By that same matrix, of course, now many things that were not 0 to begin with could have now become 0, because I am going modulo a maximal ideal, right? Or evaluating those functions at the value x. Therefore, many of them could become 0. So, what could happen to rank? It could drop, which means that the dimension of the module could increase. It cannot go down. It cannot go down, because if, right, you agree that the, if the rank, it cannot be that. So the rank after I pass to k small x, okay. So let's give this a name. Let's call this some dagger or something, right? So what we want to observe is, so maybe I'll use this. So consider dagger tensor kx. Okay. This presents not very, I'm taking liberties with the language, but I hope that is clear what I mean. It's a, what you get is a short exact sequence, not short exact, I mean, 3, without a 0 on this side. It's an exact sequence which is a presentation of that vector space. Therefore, what do I know? So I know that dimension of this thing, which by the claim above, just proved, is the dimension of the tangent space at x. Right? By that's the claim. This is the dual of this, so they have the same dimension. Okay, what is this? This is equal to n minus the rank of the matrix. I'll write now A tensor kx. Right? By that I mean I look at the matrix, just read all the entries modulo. Of course, that rank is less than or equal to R. Right? If that is, just let's understand that, it cannot go up, because if it was initially R, what does it mean? It means that all R plus 1 or higher determinants were 0 to begin with. And if they were 0 to begin with, they are definitely 0 after you pass, after you tensor. Okay, so it definitely cannot be higher. It can very well be lower, which means this dimension can, so this is bigger than or equal to n minus R. So that is this. So, right. What did we want to say? This was the dimension of X by what we proved. Right? This R stands for the rank of this matrix with respect to this quotient. Is this clear now? So we have proved this. Okay, now let's see this and that. Now it's sort of you can tick them off. We have the arguments on the board, so we just need to observe that we have them in place and tick them off. So we've done this, right? Now why should there exist a simple point? Which means there is definitely one point at which after I specialize, the rank does not go down, right? How do I find such a point? Well, one of these R by R matrices is non-zero, and and it's a non-zero polynomial function on X, right? It's a non-zero polynomial function on X. So if it is a non-zero polynomial function on X, it must be non-zero at some point, right? Because I can think of it as a function on the set of points, right? If it was zero, it would be identically zero at all points. That's not the case. So there, of course, I am using the fact that it is the thinking of them as functions on the set of points, or as a polynomial being zero or non-zero. That's the same. Okay, that is Nullstern-Satz. Okay, so since as a polynomial something is non-zero, then there is a point at which it is non-zero, and so you take that point, and there, of course, the rank, you preserve the rank even after you tensor. Right? So this is also clear. Right? And this is also clear because let's think through this. Right? Suppose some point is simple, which means one of these functions one of these R by R determinants is non-zero at that point. Right? Now call that F. Now look at D of F. That is the open subset of X where that polynomial does not vanish. Now that is an affine open non-empty subset because X belongs to that. Right? Therefore, on that, in fact, for every point on that is simple because you hit at all those points, you are going to still hit the n minus r. Right? Therefore, this is also clear. Okay, let us see this one. Okay. So to repeat, the point is that you use this. The key thing is to think of this, and you're just tensoring this with first with the quotient field. So this is very standard. This interplay between going once to the quotient field on the one hand, and on the other to various points, to various residue fields. Okay? So you are going on the one hand to the quotient field, on the other hand to various residue fields, and you are going to say that whatever I attain on the quotient field is a lower bound for the dimensions of the tangent spaces. Okay, at all points. That is this. And that whatever I attain on the quotient field, that must be equal to the dimension of X. That follows from this fact. Right. Moreover, whatever I attain on the quotient field must be attained generically. Okay, that's called. So the word generically now starts meaning to make sense. Because so generically means on an open set. So the good thing happens on a big open set. It is well behaved. This is what you're saying, right? That is this statement. You hit this dimension, equality holds, and the rank of this matrix is maximum. That maximal is hit at almost all points on an open set of points. Okay, let's do this now. Okay. So X is a simple point, right? Okay. Now, which means that there is, again, there is one of these R by R minors, which is non-zero. Okay. I claim that if so, then you can let's, for simplicity, let's say this is the first north west block of R by R minors. The same argument will hold if you can modify it accordingly. So let's, for simplicity, say this set of R by R minors was of this. It's not, there could be anywhere, right? Of that matrix is right? And as Shayanta helped us with that argument, so I can multiply on that side with a so let's see, so this is, I can multiply on this side with an n cross n matrix, and let's see, let's make it block. So this is R, right? This is R, this is n minus R, this is m minus R, right? So I make this R by R, and this is n minus R, this is n minus R. Okay, I put the inverse of this matrix here, okay, and complete it to a let's see, if so when I multiply this with this, I want to get, so let me put a 0 here. Okay, and then I don't care. I put something 0 here, and then some invertible matrix here. Okay, what I am trying to do is the following. Okay, this R by R minor is say F. Okay, now I take U to be D of F. That F, I am claiming this, that U will work. Okay, I take U to be D of F. And now I am performing these operations in the ring KXF. I am performing these operations in the ring KXF. So, since this matrix had determinant F, which was a unit in KXF, I can appropriate, it has an inverse in that way. I put that inverse here, right? And then, so this determinant has 1 over F. So I put I think any invertible matrix. Put some other invertible matrix here. So if so what am I doing? So by multiplying on the right, by an n cross n invertible matrix, I am changing basis here, right? I'm just changing the basis there, not doing nothing more. So after I do that, what do I get? I do get so this is what I have. Right? The point is, I'm only worried about I don't care about the other things, but the first R by R block, I've got an identity matrix. Okay. Now, again, I multiply by, do column operations, right? I can do column operations. Again, I'm only changing basis here, right? I'm only changing basis here. So by doing column operations, I can kill off all these, right? You agree? I can kill off the first row by just multiplying this by a suitable multiple. Kill off the second by multiplying by a suitable multiple here. Of course, this will change, but I don't care. Right? So I can assume that this is 0. So I want to emphasize that I'm only changing basis elements here. I have not done anything to basis elements here. Okay. Now, after you have done that, the claim is that this must be 0, because otherwise the rank would have gone up. Right? It's already rank R. If there was something non-zero there, it would have gone up. So that will become 0. So this is 0 is forced. This 0 is forced. Okay. So what that shows is that the images of the first let's see, is this okay, I want to say is a free module. Aha, this is not what I want. Right? All this is no good. I want that this is a free module with basis. Aha. Okay. Looks like I have to do row operations, not column operations. I thought this would do the job. See, okay, finally what we have. Let's look at why I think I don't have. Okay. What is the point now? What is my the image, right? See, the point of this is that the image is generated after I localize at F. So all this is after I localize at F. The image is also a free module generated by the images of the first R of them, right? Okay. Which means that this is a free module which is generated by the R plus 1 through R. the images of the standard basis elements okay, let's think okay, I goofed. Okay, 1 second. Let's do row operations instead. Okay, let's do row operations instead. Okay, so what I want to do is I am free to change. Okay, let's go ahead and write new row. So I'm going to write this matrix on this side. So this is my R by R matrix. This is n minus R. This is m minus R. Okay. So I multiply this by an m by m matrix, where I have an R by R column here. So row into column, I want it to be, so I put this 0 here. Of course, this I have no control over. This is some matrix like that. Okay. So now this is an invertible matrix in, all this is happening inside KU, which is KXF. Okay. Right. So what am I doing now? I am changing basis elements here. Right. I am changing basis elements here. Is that okay? Now let's see. What is the okay? Let's also see. If I change. Okay, let me just take a basis element A1. Okay, I'm going to erase this. Let me take the basis element A1 E1 plus AM EM, right? Say that's a basis element. E1 through EM are standard basis elements. What is the image of that? Right? That image is, that goes to A1 D F1. AM D FM. Right? F1, F2, Fm are those elements. Okay. So now if I change, so is that that is not what I want. Oh my God. Okay, I'll take a rain check on this, as they say. So one more time. Okay, I'll do it on Wednesday next week. Okay, that doesn't seem to work unless you see some idea. because d of that I wanted it to go to, so I wanted to change if I change I better be careful. No, do it. I'd rather do it carefully. And so let's take a rain check on that. I thought about it at home and thought that this column thing would clinch it. Didn't realize that I was doing it at the wrong end. Okay. So we do want to have this. I can assure you it's not something deep. It is just a matter of arranging the, doing the right kind of operations and seeing it. Okay, it's not. For example, I don't think it is as important as this statement here, for example. Okay, it's just a matter of getting your linear algebra and matrix right. All the same, it has to be done, and I'll do it. Okay. Now let's go to the second. This finishes modulo this goof up, which I have to clear. The first theorem, right? So there are two theorems and two general, and of course after that you apply these general theorems of algebraic geometry to the case of algebraic groups. That we have done. So I'll just look. Let's just look at the second theorem. So where is this? Theorem. So this is 4.3.6. X to y be a morphism of irreducible varieties. Again, it is easy to reduce to the case of affine, but it's important to note that you can just remove that from the condition. I mean, it's not enough. We are doing it for all varieties. Assume x in X is simple with, so let's give this a name, phi, with phi x simple in Y. The image point is a smooth point in Y, and Txx, so there is a d phi at x which takes it to T phi x y. Subjective. If this is so, then phi is dominant and separable. And the second condition is, suppose that phi is dominant and separable. Suppose that phi is dominant and separable. then the set of points as in 1, set of points x as in 1, meaning x such that x is simple, phi x is simple, and this map is surjective, is non-empty, open in X. Okay, now putting 1 and 2 together, if we call this as, if we take this condition as saying something is good, good is happening, then it's saying if something good happens at a point, then such a good thing happens on an open set. That's what we are saying, right? Because you can remove, then phi is dominant and separable, and then you can feed this conclusion into this hypothesis and conclude that if this happens, then it happens on an open set. Okay. Okay, the first thing is to, so proof. Okay, may assume x comma y are affine and smooth. Okay. Let's see why. Okay, suppose we are trying to prove the first one. Right. Now x is a, so what we need to show is, suppose I show 1 under this assumption, then 1 is shown. Right. So let us take, so I'm given this. Now, by the first, whatever we have proved already, I know that the smooth, the set of points where x is smooth and the set of points where y is, I mean set of smooth points of y are both open sets. So, given, so I can find, so let's call this y, I'll call this v. I find an open subset, affine subset of y which contains phi x and all of whose points are smooth. I can do that. Now, the inverse image of y, inverse image of v is an open set containing x. Right? Now, I can find an smooth, affine, open set U contained in phi inverse of U around, containing x and containing phi inverse of U. Right? So what do I have now? I have x sitting inside U. U is affine smooth. This is going to phi x. This is contained in V. This is affine smooth. And U going to V. Right? And now I assume I know the statement. So by this I mean if we know the statement for affine case, so in that case you would still have this conclusion, right? Because that is independent of where I look at Tx, x is same as Txu, and the map is same as, map won't change either. So you would know that this map is dominant, right? So if I take Ku closure that contains V, I mean the image of phi U closure contains V, right? Therefore, but V is dense in Y. So if phi enclosure contains V, what about phi exclosure? This contains phi U, right? Phi closure. This contains V, but V is dense in Y. Therefore, phi exclosure is equal to Y. So it's dominant, and this is dominant, and this is separable, meaning you know that Kv is an injection into Ku. That is, this is dominant and separable, which means this is an injection, and furthermore this is a separable extension. But then this is equal to Ky, and this is equal to Kx. Okay, maybe this requires just a little bit of facts about varieties that we haven't quite done. But let's for a minute assume that x and y were affine to. Okay, then can you see this? Indeed, this is, see, what is U? U is an affine open subset of x, right? Which means it's like D of f. So U is just K square bracket x localized. So you know, instead of going all the way to the quotient field, you've just inverted one element. So, but if I go all the way to the quotient field, both of them will become equal. Okay? I understand that's not very convincing, but maybe. But so you would get what? So there is no difference, right? So for the first, at least, we may assume. Okay, let's look at the second. Okay. Now, if it were dominant and separable, then this would be, it's okay. Now, then if it were dominant separable, I claim this would be I could I claim this is dominant and separable. If I look at an affine open here and an affine open here such that this goes into this, right, which you can do by first looking at an affine open in Y, looking at the pre-image, and then choosing an affine open in that pre-image, you can always find affine open such that this maps to this. And if the original one were dominant, I claim this is dominant. Okay, why? That's easy to see just topologically. Now, if this image, right, if this image were not the whole thing here, but this is dense in X, therefore it would turn out that so this meant if this is not dense, there would be an open set here, which is open in the whole thing, which would not intersect that image, right? So the image would not be, moreover, how to say, see, this is dense in X. So therefore it would turn out that X also is, the image of X cannot also be dense in Y. Okay? So there is a little bit of thing maybe to check, but that's easy to see. Okay? It would be dominant, and the maps at the level of the function fields, these are called function fields, would be the same, and therefore they would be separable. So this condition would pass directly to this hypothesis will pass directly to any affine open subsets, and then this kind of proposition would be true. But then it's true there, right? Okay, let's be careful. Okay, so maybe what we want to say is, first of all, that it is non-empty would follow, because you would get a point non-empty thing here in this already here, and therefore it will be non-empty. Okay. Now I want to say that that is open in the big one. So what now I take a point x as in 1, right? That is x here, phi x here, right, which are smooth, and that map is selected. Now I choose open sets around that, right? Then I would know that they are that thing, this thing I know is true in the affine, in the affine case. Therefore I would know that there are this good thing happens around an open set about x and phi x, about x. And but then now you can do it in now it's all right. Okay, so there is a bit to think about, but and definitely you should think about this, but after a while you should be comfortable and just write, you may assume x and y are affine and smooth. Yes, first one, yes, that's why I said to begin with non-emptiness is I just go to an arbitrary affine open, right? First to prove that it is non-empty, I first go to arbitrary. Then I know that it is non-empty there. And therefore it is non-empty to begin with, right? And then I take around that. Correct. I have to first prove that it is non-empty. And also, one second. Why am I allowed to assume they are smooth? Okay, so I am further assume that they are smooth. In the first case, I have done it because I assumed that they were smooth points. They were smooth, like u and v were smooth. Okay, in the let's do this second again. So okay, when he says this, okay, maybe he's a little loose here. I think first no, that's okay. Now I first restrict. Okay. Here, first I start with y. I'm trying to prove 2, right? General. Okay. I'm assuming that I know 2 for affine smooth case. Okay. So what I do is the following. I'm trying to prove the non-empty thing. So what I do is I look at smooth. I can look at an affine smooth, open affine smooth V. Why? Because I can first look at only smooth points. That is, I know, is an open set, not empty open set, right? And therefore I can choose an affine open inside that, call it V. Now I look at the inverse image of V. Now that's an open sub of x, right? I intersect it with the smooth locus in x that is open in the smooth locus of x, and then I choose an affine open inside that, that will map to V. I call that V, right? So, and now what we have observed is this second one will pass. The hypothesis will just pass to that. So I have affine U smooth, affine V smooth, and that map is dominant inside. Okay. Then I know that it is non-empty there, therefore it is non-empty here. Okay. Furthermore, I know that the set of points where that happens is open in this case. Now, okay, I have proved non-empty, right? You agree. Now I have to show that it is non-empty open. Okay. So now I look at a point where such thing happens, okay, right? And then I have to show this open set. I can restrict okay, I can take V to be around phi of x, smooth, affine, open, U around smooth, affine, open around x, U going to V, right? And I would know that there is an open set around x where this would be good, and that would give me the open set in x around little x, which would be good. Okay. So there is something to be done by. Okay. Well, this will take. We will not finish this within any. It will take at least 10-15 minutes, maybe longer. Okay, so it's going slower than what I thought, but it doesn't matter. We'll stop wherever we stop. Okay, so we'll continue. Okay, I have. So I will not discuss this again. So we've done this. So we go. I will clear up that that bit from the first theorem, and from this we'll do the proof, and we will start talking about Lie algebras and that particular. There is a lot there because and it's quite beautiful. Of course, this is general sort of nonsense about algebraic varieties, but there with the group action put in. With the talking about the group, there is a lot more structure, and it's the group action is there, and therefore it's much more much nicer. There's more structure to play with. So the speed at which I go, I don't think I'll be able to finish that whole section, but like I said, we'll get wherever we get. Okay, see you.